Hello, Josiah.
Morning, Manaya. And morning, Sella. Morning, Delaney. Antonio.
Morning.
Morning. All right. All right. I think it's like right on time or maybe 1 minute early. Any questions from yesterday's sample space mastery test? Did you get any questions that you wanted to go over? We could do together now. Not yet. All right. If you change your mind, just let me know. Let's look at the next lesson, next section, addition rule for probability. And good morning, Aaron. Good morning, Andrew. Before we start the new stuff, I want to ask again if you guys have any questions from yesterday's sample space mastery test. You know what? I should also talk about and announce. Yesterday, I don't think I put up our video, so Delaney, sorry about that. I'm gonna put it up today. Um,
Thank you.
yeah, sorry about that. I meant to put it up, and it was just super busy, and today's probably gonna be busy too. But I'm gonna make sure to get that up. I did get everyone's grades entered, so all your grades for we did 2 units, unit 6 and 7, are entered for last month when we did them. Um, the new one, unit 8, is for like the current month. So that'll be entered for this month 9. So we should be good there. If there's any issues, just message me and let me know. But I think everything's good on units entered now. All right. And then I'll put up today's lesson and yesterday's at the same time, I guess at lunchtime today. So this is called addition rule for probability. We're going to see a couple different rules we can use when we're doing probability problems. And the first is this addition rule. So this is going to cover what's called mutually exclusive events. With your mics off at home, do me a favor and practice saying that out loud. I know that these words are big and maybe scary, so just practice on your own. Don't turn on your mic, it's okay. Mutually exclusive. And we have to be familiar with this non mutually exclusive. So these two phrases are going to be important when we're using the addition rule. And we need to be able to like understand and know the difference between them. Here we go. Yeah, mutually exclusive and non mutually exclusive. I'm going to start with some examples. So hopefully that'll make it make sense more, and then we'll be able to define those. And there's an addition rule to use for these two cases. So that's where we're heading now. Okay, so we're doing probability problems. Um, Yesterday we did a lot of questions about dice, and so I put up the dice on the screen. Because it's not the 1950s anymore, and people don't all play cards or dice all the time. I am going to have to use more like examples about dice and about playing cards, about decks of cards. So I went ahead and put these on the screen just in case you're not familiar with a deck of regular playing cards. Here's what that looks like. These are all the cards that come in the deck. Um, we see 4 different suits. These are called suits. The rows, these are the clubs. Spades kind of looks like a garden shovel, a spade, that little upside down heart. And then we have actual hearts and we have diamonds, okay? So there's 4 different groups. They're called suits in a deck of cards. And then notice like what's in each suit or group. They go from the aces, and so, honestly, the aces are, when we play a card game, they're usually higher than a king. Like it beats a king, basically. But it also sometimes gets counted as a one. So that's why it's down here where the ones should be. So there's no ones in the deck of cards. It starts at 2, 3, 4, 5, 6, 7, 8, 9, 10. And then instead of having 11 or 12, we have a jack. Let me label them at the top. These are the jacks and queens and kings. Okay, so that's like the order. Now, we're not going to actually be like playing cards and have to know what beats what, but that's just the basic idea. The jack is kind of like an 11, the queen is like a 12, and the king would be a 13. And then we have the aces as well. But what's important to know for us, for using these for probability questions, is just like, what is the total sample space? That's all the cards we see on the screen. And then it's important to know the breakdown of what's in the deck. So these are the different numbers we've got, and the face cards. Jacks, queens, and kings are called face cards because they have, a character's face on them. So that's like an overview of what a deck of cards is like. If we were in person, I would have a deck for everyone, or maybe one for each table, so we could kind of play with them and see them in person. Here's what that looks like, though, from home. The suits are like groups. Before we start any probability, please, any questions on what this deck of cards is made up of? Please, anything at all. There's something in the chat. Nope, from Sella. Have you guys played cards? I'm assuming not, but
I play cards with my uncles.
nice, Manaya. I heard Aaron, I think. What else were you saying, Aaron?
No, I just said I played too.
Oh, good for you guys. I actually love playing cards. When I was little, like super little, I used to play an old game called Whist with my grandparents. And they would get angry at each other and like cuss at each other. And I thought that was so fun. So I wanted to play too. And Andrew has and Sella has. Okay, so it's not totally out of fashion yet. Cool. I try to get my kids to play, but they don't want to. So my own like children. Anyways, here we go. So let's try some probability. So just as a quick reminder, let me get a blank screen. Shoot, I don't think I have a blank screen. Quick refresher for Delaney and then for all of us. Let me just cross this out and we'll go back to our cards in just a sec. Just a reminder, when we're doing probability, we're looking for the target of what we want, the probability of getting a 5, the probability of having an event happen that we want. So let me write that in here. Event that we want. That's our target, and that's over the total, which is all the events that could possibly happen in that scenario. So I'm going to say all possible outcomes, all possible events. So those are the two things we have to kind of look for in all of our questions. What's the event that we want? That'll be in the question. And then we have to read between the lines to find what's the total, all possible outcomes. I think it was Sella yesterday who said outcomes. Good. And remember another name for the total? This is called the sample space. So that's just another name, another definition that we'll use for all possible outcomes, sample space. I'm going to leave this on the screen in case anyone's taking notes on that. That's what probability is. So it's a fraction, the target over total. It's the event that we want. And there might be more than one way to get that event happen. Yesterday, when we did dice problems, there's usually just one way, right? What's the probability of rolling a 2? Well, there's only one 2. Let me do that example. Probability of getting a 2 with a dice. Well, since there's only 1 2 on a dice, that's our target on top, 1, because there's one way to get it. How many options or possibilities are there when you roll a dice? 6. But now we're going to expand that where there's more than one way to get that target for our probability on top. Okay, so let's go back to the deck of cards. So let's do some simpler ones to start with. Suppose we pick one card at random from a normal deck of cards. So let's say below here, I'm going to write out some example questions. Probability, that's the P, probability of picking one card and getting a 3. I just happened to write it underneath the 3s. I didn't mean to. Probability of picking a card out of all these cards and getting a 3. Well, let me ask you guys, how many 3s are available in a deck of cards? I see one answer. Let me check and see what you guys came up with. 4. Good, Sella. Yeah. And this is another reason I wanted it visually, so we could see it and not have to guess. So here's all the 3s that Sella's noting are there. There's 4 different 3s, right? 3 of diamonds, 3 of hearts, 3 of spades, and 3 of clubs. So that's our target. There's 4 different ways to get what we want. And how many total cards are in this sample space? That's our bottom number for our probability for our fraction. So we're going to use this number a lot today. Let's see. Someone put it in the chat already. Notice that each row, each suit is the same number of like options, right? Ace, 2, 3, 4, 5, and up. So I think there's 13 in each group. And if there's 4 groups, that's 4 times 13. So it should be 52. Let me see what you said. Yeah, Sella's on point. So there's a total number of 52 cards in the deck. All right, I've already lost somebody. 4 out of 52 would be our probability of getting a 3. And like yesterday, we're going to reduce that fraction down, and we're going to find the percentage. So reduce the fraction whenever possible. Let's divide the top and bottom by 4. We get 1 over 13. So here's the answer that Edmentum would want in a fraction form, 1 over 13, or divide it to get the percent. You divide and you get a decimal, of course, 0.07. I'm going to say a few of them, 769. Now remember, it's the first 2 that give us our percentage. So it looks like it's 7%. We have to do our rounding though. So let's go ahead and say 7%, but it would be 7.6. This 9 is going to round it up, guys. So that becomes 7.7%. Good. You're close, Sella. It's not 77. We need to keep the. Oops, there's Delaney. We need to keep. We're looking at just those first 2 places. Always, it's those 2 out of 100. So I see where you got the 77. I got it too, but it's 7.7. Good question. Does that help, Sella, or not yet? Not really. Let me change my color real quick, guys. So when we're doing our decimals and our percentages, always do the dividing. That's where you got the decimal from. And then we look at those first 2 spots. It's those 2 out of 100. So if I was going to, I guess, cut a corner here, I might, without doing the rounding and the point on all that, I would just say 7%. Because when you look at those first 2, that's all we have is a 7, right? So 7% would be a safer thing to say. But it would be more precise to say 7.7 because that's almost 8, right? That's like even higher. That's a little higher than 7%. No problem, Delaney. No problem. Thanks for coming back. Let's practice some more so we can get some more practice with our decimals as well, guys. So let's say we did another probability. next to that one. Probability of not getting a 3, but let's say probability of getting a diamond. So pick one card out of the whole group. What are the odds? What is the probability we get a diamond? So we need that top number and bottom number. Bottom number is still 52. Sample space is 52. But how many diamonds are there? Because all of those diamonds would count as a win. So we find those and count them up. Someone's already said it. 13. Good. Yeah, each row has 13. So there's 13 diamonds, 13 hearts, 13 all of the suits. So we're looking at 13 out of 52. And if we reduce that, we actually get 1/4. Divide 1 over 4. And you get the decimal 0.25. So because it's a point and then 25, the 25 is our percent, 25%. Good. Good job. Good job, Sella. So there's a 25% chance we could get any diamond. In fact, there's a 25% chance we pick one card and get any of the suits. So if I asked about clubs, same thing, 25% because there's 13 out of 52. So now we're going to bump it up a notch and not ask about a single outcome. So both of these examples, I asked about a certain number getting a 3 or about a certain suit getting a diamond. But what if our question was, what is the probability of... Okay, I'm covering up one of the questions. Down at the bottom, probability of getting a 5 or a 10. A 5 or a 10. Both of those would count as a win for us. So we're interested in picking one card, but having it be a 5 or a 10. So this time, how many different ways are there to get what we want? There's 4 5s and there's 4 10s. So nice. Aaron, high five, dude. Boom. 8 is our target because there's 8 ways to get a 5 or 10 out of the total 52 still. That's not going to change. It's always out of 52. So there's our first answer, and that is correct, but we want to reduce it down. And what does that come to? I think it's 2 out of 13. And how do we find that? Let's just divide by anything that is common on top and bottom. So we could divide the top and bottom by 2 and get 4 out of 30. No, 4 out of 26. 8 divided by 2 is 4. 52 divided by 2 is 26. And then we can do it again because they're both even. And we get 2 out of 13. Okay, we do our division. So here's that in fraction form. Divide it and we get 0.1538. We're looking at those first 2 spaces. So it's basically 15%, but let's keep 1 point on there since it's not exact. So we would say this is 15.4%. Good job, Sella. You're getting it. Nice. Good to see. So what's different about this question, this example, is that it wasn't just a single event that would work for us, right? It was 5 or 10. And the word "or" is the key thing that stood out here. This event A or this event B, 5 or 10. I'm going to move this thing out of the way quick. Let's try the next one. And this is pretty low down. So maybe some people it's cut off. I'll write it above. Okay. So we're doing find the probability of a heart or 2. I'm going to put it up here on the left side. Probability of a heart or a 2. Okay. So now visually on the screen, we can like locate all those. We have got hearts right here in purple, or any of the twos would work. So I'm going to circle those as well. And this is where things get a little weird because look at that. There's one card that is both a heart and a two at the same time. This guy. Sella and Aaron, high five to you both. They both said 17 out of 52. Let's double check. I think you guys are on point. So where's that 17 coming from? Visually, we should be able to count up all of them that I just circled. I'm going to go ahead and like check them off. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Ooh, interesting. Let me double check my work. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Okay, when we count them up visually, we see it's 16 total. I think I know where that 17 came from. There's 4 hearts. This is great. Honestly, I'm glad you guys answered the way you did because there's not 4 hearts. There's 4 twos and there's 13 I can't think today. I'm sorry. Four of the twos and 13 hearts. And that's where the 17 came from, right? 17 total. But the issue is this card that I pointed out, the 2 of hearts, it counts for both. So what happened is it was double counted when we just added up 4 in this group, 13 in that group. And that's the issue. We don't want to double count the stuff that is like could qualify as both. Yes, Sella. Yes, exactly. It's 17 because we that one card there, the 2 of hearts, counts as both. And this is where those terms from that I mentioned earlier come into play: mutually exclusive or non-mutually exclusive. Let's talk about those now. And then on the next screen, I want to define them. So, looking at these 2 examples we just did, probability of hearts or twos. This is non-mutually exclusive because, well, actually, you know what? Let's back it up. Sorry, guys. Let me back it up. Look at the example, find P, 5 or 10. 5s or 10s. So my question, guys, is can you pick a card and have it be both of those at the same time? No, right? You can't be a 5 card and a 10 card at the same time. Kind of by definition, right? They're just 5s or 10s and that's it. You can't be a 5 or a 10 at the same time. It's either one or the other. The fancy math word we're going to use for this situation when you can't be 2 different things at the same time is mutually exclusive. Let's talk about that phrase, that name. Mutual means together. So like, you 2 of us as 2 people, if we did something together, it's a mutual decision, mutual means done together. And exclusive means like, I think of it as like an exclusive club. Like you got to be a VIP to get in. So exclusive means it's really special. So this means together, mutually, they're both very special and unique. Together, they are unique. Meaning they're both unique. So 5s and 10s are mutually exclusive in a deck of cards. I'm going to change to green on the top left where we talked about probability of hearts or twos. Now, hearts or twos are different because there's this two of hearts. So if I ask about hearts or twos, this is not or non mutually exclusive. Because you can be a heart or a two at the same time. This card right here in green is both of those at the same time. So here's where the addition rule kicks in. And I like how Aaron and Sela first solved that problem because that is how we can solve mutually exclusive problems. We add the two probabilities. The only issue is if there's a card or an outcome that can be both events at the same time, event A was hearts and event B was twos. And there is a card or like an outcome that meets both of those requirements at the same time. So we need to subtract that one out of our probability. So 17 over 52 minus 1 over 52 gives us the proper probability for that scenario. So mutually exclusive. I already defined this, but I'm going to write it again a little cleaner, a little more formally. Mutually exclusive means two events cannot happen at the same time. Or simultaneously, right? It can't happen simultaneously. Cannot happen at the same time. To help you remember, I think the best way, at least for me, is thinking together, mutually. They're exclusive. They're VIPs. They can't be the same thing. They're unique from each other. Totally unique outcomes. And our example is picking a 5 or a 10. So when this is the case, if we're asked to find probability of A or B, here's our formula or our rule. Probability of two events, A or B, it's simply adding the two separate probabilities. Probability of A plus probability of B. This is the example that we did of picking a 5 or 10. Fives, let me put an example below in a different color to help differentiate, just to remind you and connect it. So, for example, probability of picking a 5 or a 10 from a deck of cards. There's only 4 5s out of 52, and there's 4 10s out of 52. We added those together for 8 out of 52. And then we reduce it down and we find the decimal and all that. But the point is we just add the two separate probabilities. The exclusive probabilities. Separate. Okay, so what about the non-mutual exclusives? When we said, let's pick a heart or a 2. Well, non-mutual exclusive means they can happen at the same time. The two events, there exists an outcome, at least one, where they are the same thing. Let me write that, and then I'm going to check the chat. Not unique because there's at least one case where they're the same thing. And the example was picking a 2 or a heart. So our formula or our rule for this, I hope you guys can see it. It's not too low. Tell me if this is too low and you can't read what I'm writing right now. Probability of A or B when they are non-mutually exclusive is adding the two separates, probability of A plus the probability of B, and then we have to minus probability of A and B. What we're minusing is that overlap. We're minusing out the two of hearts, essentially. Good. Intersecting. I like that word intersecting. Sella said in a direct message, non-mutually exclusive means they're basically intersecting outcomes, like we saw with the two of hearts. That's like an intersection of the two events, A and B. So let me put in our below here. Let's connect this back to the card example. So in the example, we had probability of a 2 or a heart. So we add the two separates, 4 out of 52 to get a 2, plus 13 out of 52 to get a heart, and we have to subtract that overlap. And the overlap is 1. How many cases are there where it's a 2 and a heart at the same time? It's only 1 out of 52. Now, if we're doing a problem with cards or dice or something more tangible and smaller sample space, then doing it visually like I was doing on the screen is not too big of a deal. We can see the overlap. But we need to be ready to use these two formulas. I'm going to circle both of the official formulas. So make sure these are in your notes. And the definitions for mutually exclusive and non-mutually exclusive. This is how we went from 17 out of 52 to 16 to get that precise probability. Now, how are we adding those fractions? Just a quick reminder, as long as the bottom number, the denominator is the same to each other, just add and subtract across the top. 4 plus 13 minus 1 gets us that 16. And then, of course, we would reduce our fraction and find the percentage and all that. Good. Yes. Good, Sella. So next up, it's 10:30 now. Next up, I've taken questions from Edmentum, I think. And I want to show you what these are like and help you reason these through. We have to decide in every question, is this a mutually exclusive scenario or non-mutually exclusive? And then it's just a matter of, picking the right formula and combining our numbers and being done. I think the hardest part is probably just deciding, is this mutually exclusive or not mutually exclusive, and then using the correct formula for that case. Sometimes they may be more intuitive and make more sense on their own. Sometimes it might be a little trickier. So I'm ready to try a harder problem with you guys. I'm going to wait 10 seconds in case people are writing. And if you need more time, just tell me. It's okay. Here we go. Okay, now this is a lot to write down. So for this lesson, if you want to just take screenshots of the word problems, that's okay, because I don't want you to spend like 10 minutes writing. The math is more important. The thinking about it is more important. So just work through it with me. Take screenshots or pictures with your phone. Katie is playing a game using a 26-card deck. 26-card deck that contains the black suits of cards. So she's only playing with literally half a deck. The 13 clubs and 13 spades. That's in our sample space right now. She can score bonus points if she draws a face card on her next turn. Okay, here's the actual question. What is the probability that Katie will draw a king, a queen, or a jack on her next turn. That's the actual question. So let's figure out the sample space of this scenario. 2, we need to figure out, is this a mutually exclusive or non-mutually exclusive scenario? Can a card that she draws be a king and a queen at the same time? A king or a jack at the same time? So first off, what is the total sample space? Well, it says at the beginning it's a 26 card deck. And then they tell us some details. It's all the black cards. So 13 clubs, 13 spades, 26. Oh, Sella is totally on it. So Sella's already zooming past me. Let me catch up to you. So if there's 26 cards total and our desired outcome, event A is king, B is queen, and I guess event C would be getting a jack. So any of these is a win for us. Now, mutually exclusive. Can I be a card from the deck and be a king or queen or jack at the same time? Are there king, queen, jack cards that are like the same card? No. Cannot be these events at the same time. So that means this is mutually exclusive. Yes. This is a mutually exclusive set of events. So we simply add up the separate probabilities. So we need to know, okay, what are the odds of picking a king out of these black cards? Well, how many kings are there in just the black cards? Let's go back to the visual real quick. Not looking at the red ones. They don't exist here. So there's only 2 kings out of 26. There's 2 queens out of 26. So Sella, you're totally on it. Yes, you were right earlier. And 2 jacks out of 26. See how these are, and I'm going to label this as well. This is the probability of king, probability of queen, and probability of jack, all added together. There's nothing to subtract because there's no overlap or intersection. So we add across the top, we get 6 out of 26. Nice job, Sella. And let's finish this one properly. So we divide, let's say 6 out of 26. Reduce that down. What can I divide the same number by for 6 and 26? At least we can divide 2, right? So divide the top by 2 and the bottom by 2, 3 out of 13. Divide that for the percentage. Try it at home. I got 20.23. And it goes on, 0, 7. So we're looking at those first 2 spaces. That's 23%. And we could say 23.1. Since we have a decimal, we want to include at least 1 point of that decimal, 23.1% chance. Ooh, yes. Sella is like on fire. 3 out of 13 if we reduce it, 23%. Good. So in this case, they were mutually exclusive. You can't be a jack and a queen and a king at the same time, so we just add up the separate probabilities. Okay, just in case you want a picture of all this together, here's that problem finished. 2 out of 26 added up, 3 times for 6 out of 26. And we got a finally 23.1% chance. Okay, I want to try another one with you guys. This one's pretty tricky. Of a group of 500 people, 60 are fit enough to climb Mount Shasta in California. The group has 300 women and 200 men. 12% of the men are fit to climb the mountain. What is the probability that a person picked at random from the group, so one person out of that 500, is a male or is fit to climb Mount Shasta? So the either or that they're asking about, those are the events. Event A is male, fit enough to climb, is event B. Picking one person out of that 500. So my question to you guys, first question, I know there's a lot in this question, but to break it down, the first thing we should ask ourselves is, can you be event A and event B at the same time here? What are your thoughts? Can you be a male and be fit enough to climb Mount Shasta in this scenario? Does it sound like you can be or you can't be? Can event A and event B happen simultaneously? That's telling us if it's mutually exclusive or non-mutually exclusive. Let me rephrase that. Can event A and event B happen at the same time? I see one comment. Let's read it again. I see 2 comments. There's 500 people. We're good there. It says 60 of the 500 are fit enough to climb. And then they tell us a little bit of a breakdown. There's 300 women in the group and 200 men in the group. And then it says 12% of the men are fit to climb the mountain. Before we do anything else, we might not even need this information, but I want a fuller picture when I'm working with this kind of stuff. So let's figure out, what is 12% of the men? How many of these men are supposedly fit to climb the mountain? Let's do that right here. 12% of men. How can we find that? We need to multiply the men by 12%. I'm going to convert 12% to a decimal and multiply that to the men, which is 200. $24 even. So that means there's 24 men are fit to climb the mountain. Okay, here come a lot of more comments coming in. So we need to go back to that initial question. Is this mutually exclusive or not? Can event A and event B happen simultaneously? Yes, it's telling us without being very direct, right in the middle, it says this much men are fit to climb the mountain. Men are fit. So there's some amount, and we just figured it out. It's 24 exactly. So because these events happen at the same time, happen together, happen at the same time, this is non-mutually exclusive. Shoot, I'm sorry, non-mutually exclusive. The struggle is real for trying to write fast here. Sorry, guys. Mutually exclusive, non-mutually exclusive. And the point is that we need to subtract out the overlap in this case. So we're going to do the separate probabilities of probability of being a man or male plus the probability of fit to climb minus probability of both of those events, the men that are fit to climb, because we don't want to double count that little cross section, that intersection. So we're subtracting out the men fit to climb, the A and B, the two events at the same time. Okay, so let's check your guys' chats. Thank you all for responding. Ooh, some people are like solving it. Okay. Oh, Sella. Okay, she's back to grab a computer. Yes, Aaron. That's what I was hoping you guys would see. And Sella, that yes, these events happen at the same time. And that middle sentence is the part that's kind of telling us that 12% of men are fit to climb the mountain. So let's see if we can put these together. Probability of just being a male. Help me out, guys. How many men are there total? And how many total people are there? It says at the top, there's 200 men. And how many people total? There's 500 people. So down below now, probability of just being a male, 200 out of 500. Good, Sella, thank you. Now, next question. We need the second probability, probability of fit to climb. Does it tell us that directly? How many people are fit to climb? 60 are fit to climb. So the probability of reaching in the box, so to speak, and getting one person that's fit to climb is 60 out of 500. And now, finally, we have to do this subtraction here. I'm underlining it. Minus the probability of men fit to climb. We solved that in the middle and found it's 24 men are fit to climb. So minus 24 out of 500. Good. Good, Sella. So now we've got it all set up. 200 plus 60 minus 24. It's the probability of men plus probability of fit to climb minus both of those at the same time. So that is 260 minus 24. 236 over 500. And I guess we should reduce it, even though it's going to be kind of weird. So let's divide the top and bottom by 2. 236 divided by 2. 118. I guess they're both even still, so we can keep going. 118 divided by 2 is 59. 250, I think, is 125. And I think that might be it for reducing. Yeah. So let's now figure out the percentage. So 59 divided by 125. 47.2. The decimal is 0.472. We're looking at those two spaces, 47.2%. It's almost half. Because we're looking at just getting any random male or anyone who's fit to climb, including the women fit to climb, basically. Good job on the percentage, Sella. Ooh, and you did it even with decimal. Nice. Look at that. And so, was that a direct message? I hope this is okay. I wanted to show everyone what Sella did. So Sella did the decimals of each one of these separate probabilities and then added those up and subtracted out the overlap. That's fine too. So down at the bottom where I have it 200 over 500 plus 60 over 500 minus 24 out of 500, you can actually divide those right away if you want to and get the decimals. That's what Sella did here. And then finally got her final answer. Okay, I want to try another problem. Oh man, it's already time to go almost. Take a picture of this if you haven't already. We're going to do at least one more together. I'll wait 8 more seconds. Here we go. A school choir has 80 students. 36 of them are in the 7th grade. 40 students in the choir are girls. 18 of them are in the 7th grade. So that means 18 girls are 7th grade. What is the probability that a student picked at random from the choir is either a girl or a 7th grader? So there's our event A and event B. So no boys and no grades other than 7th are interesting, are win or a success, a target for us. Okay. Can you be both of these events at the same time in this scenario? Yes. There are girls who are 7th graders. It tells us back in the middle right here 18 girls are in 7th grade. So this is non-mutually exclusive, which means we have to subtract out that overlap of 18 girls basically, because we're going to count them twice if we don't do the subtraction. So probability of being a girl plus probability of being a 7th grader minus probability of 7th grade girls. A and B. 7th grade girls. Question, Bailey? Okay, it's all good. If you do, please tell me. So let's figure out the separate probabilities and then just put them into the formula. Probability of girls. It says 40 students in the choir are girls. So that's 40 out of 80. 7th graders. It says 36 of the choir people are 7th graders. And then we minus out those who are both girl and 7th grade. So minus 18 out of 36. Or sorry, 18 out of 80. So 40 plus 36 minus 18. That minus 18 are the ones who are both events at the same time. Good. 40 plus. You said 40 plus 80. Not sure if I follow you there, Salah. I'm sorry. 40 girls, 36 7th graders, and 18 who are both. Notice this one. If you get, like, if it doesn't seem to make sense, if we do our problem and then it's like almost all of the people or all of the subjects at once, then maybe we were supposed to subtract out and we didn't, because 40 plus 36, that's 76, which is like almost everybody in the choir, right? So that means we probably didn't subtract out the overlap, the intersection of minus 18. Don't be sorry. You didn't do anything wrong. I appreciate you trying and following along and putting your thoughts in there. I really do. So 58 over 80, let's just divide it. 58 divided by 80, 72. Yeah, good. So we do our dividing and we get 72.5%. All right, let's do one more. Okay, 27 players trying out for the basketball team. 8 of the players are more than 6 feet tall and have good aim. What is the probability that the coach would randomly pick one player over 6 feet tall or a player with good aim? And then at the bottom it says, assume that no players over 6 feet tall have good aim. Interesting. So, you know what can help when we're trying to figure out what's going on with these kinds of questions is drawing a Venn diagram. So I'm going to look at the top again. We know that there's 27 people trying to out for the basketball team. And then we're breaking them into these two groups, over 6 feet tall people and good aim people. So there's 20, here's a picture that might help. 27 players total, or people total. And if I were to put them into like bubbles or groups, this will be our over 6 feet tall group, and overlapping that is the good aim group. It says that there's 8 who are more than 6 feet tall. So in my first bubble, there's 8 people, and 7 people have good aim. Now, those only add up to 15. What is the probability that the coach would randomly pick a player over 6 feet tall or a player with good aim? But then it says, assume no players over 6 feet tall have good aim. Huh. Assume no players over 6 feet tall have good aim. So that means there's no overlap. Yeah, you're right. 8 out of 27 would be the 6 feet tallers. Let's do them separately here. Probability of over 6 feeters would be 8 out of 27. Probability of good aimers would be 7 out of 27. I guess because the last sentence is telling us assume no players over 6 feet tall have good aim, I think it's telling us right off the bat that there's no overlap, meaning this is a mutually exclusive scenario. So if our goal is to find the probability of anyone who meets either of these requirements and there's no overlap, that means there's nothing to subtract out. So that means we add the separate probabilities. 8 over 27 plus 7 out of 27 is 15 out of 27. We can, I know that's kind of low on the screen, sorry. So we add the two separate ones right here. and we get 15 out of 27. That can be reduced if we divide by 3, so 5/9. And then that would be our fraction answer, 5/9 chance. Divide it for 55.6 percentage for the percent answer. Good. Good, Sella. Good job. This one was tricky. I was expecting there to be overlap here in the middle of my Venn diagram, but I didn't read the question properly, did I? Until I got to the end. Assume no players over 6 feet tall have good aim. I think it's kind of a weird question because it's like, where are the leftover players? But either way, I think we did that one right. So look for, in the scenario, is there overlap in that scenario? Is there not? If there's overlap or intersection between the two events, we have to subtract out the overlap. That's the main takeaway from today. I think it's time to go. Let me mark down your guys' attendance. Homework is to try doing. I realize not everyone tried yesterday's yet. So we're on the first 2 mastery tests in Edmentum. Today is the addition rule for probability.